So this really just carries on from yesterday's theory. So sixth type of trig integral is using the t-results. Now, using a t-results means we can turn a trig function into a polynomial, basically. So a reminder, if t equals tan x on 2, that's our basic t-result, then we know sine x is 2t on 1 plus t squared, cos x is 1 minus t squared, 1 plus t squared. We mainly use these for just integrals that involve sine and cos. But if I'm going to do a substitution, I've got to work out for the derivative as well. So the t dx half sec squared, which is a half of 1 plus tan squared, which is a half of 1 plus t squared. So now I've got a t result, but let's rearrange it to make dx the subject. So now I've got something I can substitute in. So my t result for dx, 2 to t on 1 plus t squared, which is nice because again you'll notice the denominators are sine, cos, and the dx is all the same. So we get something like this. Involves a cosine function. There's nothing on the top I can turn into the derivative or anything like that. So this is where the t results would be useful because I can turn this into a polynomial function. Now I don't have to go through all that working out each time. Just like when we quote the t result for sine or cos, it's fine to quote the t result for dx. So let's sub it all in. So dx 2 to t on 1 plus t squared, cos 1 minus t squared on 1 plus t squared. So basically multiply everything by 1 plus t squared. Because as I say, the denominators are all going to be the same. Just got to remember to multiply any constant we have there by 1 plus t squared. So I end up with 7 plus 7t squared. Tidy it up and we just end up with a nice standard integral there of, what's that one? We've got an a squared plus inverse tan. Inverse tan. So we've got to remember inverse tan, 1 on a goes out the front as well. So we'll have 2, and then it'll be 1 on square root 13, inverse tan of t on root 13, but of course we're going to substitute back into t. T was tan x on 2, so that would be my answer. Now, don't make the mistake of moving the 2 to the denominator. Remember the x on 2 is in the angle, so we leave it in there, and that's over the square root of 13. Now, it doesn't have to be used for tan x on 2. I mean, I could say t is tan x. Now, if t was tan x, what would happen to my derivative? We'd end up with dx is dt on 1 plus t squared. So basically, if I'm going to use a t result, I could always use it for tan of x on a, depending on what the angle is in the question. So to generalise that, go through the whole derivative there, we end up with the derivative would then turn out to be a to t on 1 plus t squared. So when we did our standard one of x on 2, it was 2 to t on 1 plus t squared. Notice the a's match. Okay, said today was going to be a quick one. Only a handful of questions as well.